So in the previous video, we looked at how we can classify matter into hadrons and leptons, baryons and leptons, okay? And in this extra video, we are going to look at how we factor this in when we write a chemical equation of nuclear reaction. So previously, you may have already known that nuclear reaction must obey the conservation of proton and nuclear number. This is the very basic. It should also obey the conservation of charge. But there are two more numbers that we can introduce into the combination, which is baryon and lepton numbers. So the number of baryons before and after the reaction must be the same, and the number of leptons before and after the reaction should be the same. Okay? And also energy must be conserved. So if you think about the annihilation example, although the mass is gone, but it converts to energy. All right. So today we're going to look at how to assign baryon and lepton numbers. Okay. So we're going to look at baryons. So the charge of baryons have a few possible combinations. So if you look at what makes up a baryon could be a proton, it could be a neutron. Okay. So the charge can be positive 1 is a proton. So I write down possibility. And proton, the charge is positive 1. And neutron, the charge is no charge. Okay. You can also have the charge of negative 1. For example, your sigma minus. So again, don't be too stressed out about these fundamental particles. Okay. What you just need to know is that all the charge is possible. You need to look at the constituent box. Okay. So likewise, this one also can have positive 1, 0, or negative 1. Okay, depending on the combination. So just a reminder, baryon here consists of 3 quarks. Meson here is 1 quark, 1 and quark. Okay, so this is a baryon. So the baryon number is 1. Meson is not a baryon number is very easy one. Just ask yourself, is this a baryon? Does it have 3 quarks? Right? So from here, electron, I think we all know the electron charge is negative 1. I mean, positron has positive 1 e, but we are focusing on particles here. Okay, and the electron neutrino, the charge is 0. These two are not baryons, so the baryon number is equal to 0, baryon number is 0. They are all not baryons. Okay, so the baryon number should be conserved. Okay. The second thing that should be conserved is the lepton number. What is lepton number? Lepton number here, baryon is not a lepton. So again, just to remind you, this baryon here it interacts with strong force, and it consists of 3 quarks. Lepton number here does not interact with strong force. So this lepton number is 0. But the 2 other leptons, which is your electron and the electron neutrino, this L equal to 1, this L is equal to 1. Okay? These are already fundamental particles, so there are no fundamental constituents. Okay? So just a reminder, although I've written it on top, that the fundamental constituents of baryon will be 3 quarks. Okay, and then this one will be 1 quark and 1 and 3 quark. Many possible combinations. I'm not going to list down all of them. All right. So now we're going to look at how to balance the baryon number and the lepton number in the most famous or most important equation in the syllabus, which is the beta plus and the beta minus decay. So the beta minus decay, okay, so generally speaking, when we undergo that reaction, then you expect to have a beta minus or electron number with the mass number 0 and the proton number of negative. Okay. So the way I think about it is, how do I know whether it's neutron to proton or proton to neutron? I have to balance off the charge, right? So I can balance off the charge by putting the proton here and the neutron here. Because if I swap places, they don't balance, right? So if you look at this, right, it seems on first sight that the numbers are balanced. So the proton number is balanced. 1 is 1 plus 0. The nucleon number is also balanced. Nucleon number is 1 plus 0. Proton number is balanced. 0 is 0 plus negative 1. Okay, so all the numbers are balanced. All right. Okay, so this one is balanced, right? And this number is also balanced. So let's look. First number would be nuclear number. Okay, I'm doing this for the benefit of your friends who may not take chemistry. Okay, so the A here, this is 1. 1 is equivalent to 1 plus S. No problem. Okay, and then I'm going to move on to the proton number. Proton number is Z. Z here would be 0, which is 1 plus negative 1. So it seems that things are fine until we check out the baryon number as saying. So is neutron a baryon? Yes, neutron is a baryon. Is proton a baryon? Yes. Is beta a baryon? No. Okay, things are still balanced. Okay, whatever I have on the left is the same as whatever I have on the right. But what about the lepton number? L. Okay, so when you think about lepton number, neutron is not a lepton. Proton is not a lepton. But our beta minus, which is actually an electron, is a lepton. GG is not balanced. So if you just keep your beta minus decay equation like this, we already know the problem because it's not balanced. We know that there's another particle, and that's how we know that there has to be another particle at the back to balance this. So I need to add this negative 1 here in order to balance this one, in order to balance my lepton number, okay, or to conserve my lepton number. Is to conserve lepton number. So I need to put an anti-lepton here. Negative 1 is anti-lepton. The negative 1 here shows anti-lepton. Didn't mention previously just now in the table, but whenever we put a negative before the number, it shows an anti-particle. Okay, so what we will have here now would be the electron anti-neutrino. Electron anti-neutrino. What is the nuclear number? 0. What is the proton number? 0. What is the baryon number? It ain't a baryon, but it is an anti-baryon. So when you balance, right, or let's say, for example, you are asked to normalize the equation, okay, always think about how you must pair a particle with an anti-particle. So this one is particle, which is actually an electron, right? Okay, so you must pair it with an anti-particle. Why? To conserve the lepton number. Okay, and also at the same time, we have the last number to talk about, which is charge. So I'll continue here. Charge number, this is Q. Neutron got no charge. Proton charge is +1. Electron charge is -1. And our lepton charge, our electron anti-neutrino is 0 because it is a neutral. Right? So you can see all the numbers, AZ, DLQ, all balanced. All right. So what about beta plus? Okay, so for the beta plus decay, what we will do is we will swap the proton and the neutron. Okay, so let me start by writing that first. We're going to look at the beta plus decay now. So previously the beta minus, we have an electron as a product. So for beta plus, we should have a beta plus or a positron as a product. So this is my beta plus particle. The neutron number will be 0, but the proton number will be 1. I will name it now. This is my positron or my anti-electron. So in order to get this combination and to balance my numbers, I should have a proton here decaying into a neutron. Yeah. A proton decaying into a neutron. So let's go. We have the nucleon number. Nucleon number here would be Z. So the nucleon number is 1. 1 become 1 plus 0. Okay, we have okay. Then we will look at the proton number, which is Z. Proton number is 1. 1 will become 0 plus 1. Okay, no problem. Baryon number 1. This is a baryon. Proton is a baryon. Neutron is a baryon, but positron is not a baryon. Okay. Lepton number. Proton is not a lepton. Neutron is not a lepton, but positron is a lepton. But because it is an anti-particle, so it's actually negative 1. Then it's negative 1 here to show you that the positron beta plus is an anti-particle or anti-lepton. So because of this, we need to bring in a positive 1 to counterbalance that everything here is 0. Then you know what that is? That would be the electron neutrino. This is a particle. Okay. So again, to balance this, beta plus is your anti-particle, it is your positron. Okay, that's why this electron neutrino will be particle. Okay, so compare and contrast with this one. This one electron is a particle, electron neutrino, antiparticle. Then here would be antiparticle plus particle. Just so that everybody is balanced. Once again, just let's check the charge. Proton is 1 plus, neutron is 0, positron is 1 plus, okay, and this one is 0. So everybody is once again balanced. All right. So this is how we know the existence of this third particle. Previously, we didn't know because we didn't know this idea of lepton and fundamental particles. But now we do. Okay. So sometimes they can ask you to balance the equation. Sometimes they can ask you to name the missing particle, that kind of thing, right? Another thing that I should point out is that there's some hot conversion that is happening within our proton and neutron. So for example, a proton is up, up, down. But a neutron is up, down, down. So for beta minus, we will have the we will have the down quark transforming into up quark. Down quark transform into up. Okay, so I will write a note. And this one, it's down quark becoming up quark plus beta minus plus electron and neutron. Is this number balanced? Yes, also balanced. Because if let's say you were to do the process, I do for you. I will do the process for you. Okay. This is down, so this one will be 1/3. Okay, and then the charge of down is negative 1/3. Okay, up quark is 1/3. This one would be positive 1/3. Beta is 0, negative 1. So positive 1/3. No. Up is positive 2/3. Okay. So we go proton number, neutron number, baryon number, lepton number, charge. Okay. So the proton number, the down part is 1/3 of the proton. So 1/3 of a neutron. It is 1/3 plus 0 plus 0. Okay. The down part is negative 1/3. So this one will be positive 2/3 plus negative 1. That's 0. Still balance. This baryon, this is 1/3 of a baryon. This is 1/3 of a baryon, 0, 0. Not baryon, not baryon. Not a lepton, not a lepton, lepton, and lepton. And the charge here will be negative 1/3, becoming positive 2/3 plus negative 1 plus 0. Okay? So the numbers are always balanced, right? Just know that the down part, okay, the proton number is negative 1/3. These are all 1/3 because it is 1/3 of a proton or 1/3 of a neutron. Okay. So I'll write this down. This one is 1/3 of neutron. Okay. And then the negative 1/3 is to correspond to the charge. Proton number corresponds to charge also, right? All right. So actually what you really need to know that they tend to ask is not so much as to write the equation and show the balance. Although they can ask you that, but you should just understand that this one is down to up. Okay. So similarly speaking, if I go from proton to neutron, I'm not going to repeat again, but here would be up, up, down. Yes, up, down, and then this will be up, down, down. So we are going from up to down. Yeah, so for beta plus, it is up to down. For beta minus, it is down to up. The quark transformation. So I think if you can write out this equation, the rest is just infer. You can infer the information from the equation. All right, don't worry too much about it. Okay, so one last thing before I conclude the video would be, when thinking about this equation, there's always this property that students tend to forget, which is the beta particle having a range of kinetic energy. So I will write here in purple. So here, beta decay or beta particles at a range of kV. Alpha don't have, gamma obviously don't have. Okay, so only as far as we know, beta particles have a range of kV. Why is that? Because the kV is shared with the other lepton. Whether that lepton is electron neutrino or the electron anti-neutrino. Okay, the electron neutrino or the electron anti-neutrino. Because their masses are similar, so during this decay, when they separate, they will take a portion, they will share the kinetic energy. This will not happen for alpha because the mass difference of alpha and the parent and daughter nucleus is very big. So normally this decay doesn't happen in isolation one. This one is inside a big nucleus, this is inside a big nucleus. So their kV is very small. And alpha tend to be alone or with gamma, and gamma has no mass, so it can't share the kinetic energy. So only beta has a equivalent sister particle, which is the neutrino, to share the kinetic energy. Okay. I throw back a bit. So here is an alpha decay, and you can see that these two are very massive. So the alpha particle will receive the kinetic energy, and it will be more or less one value. Okay. Whereas for your beta decay, although the proton and neutron is embedded inside the decay. So for example, this one, you will have a neutron becoming proton. You see the 6 becomes 7. This one, proton become neutron, 12 become 11. Okay. This one are still much more heavier than the electron and the electron neutrino. So they will share, these two will share the Ke. This alpha particle got no one to share, so it takes all the Ke. That's why beta have range of gamma is light. Light has a constancy, and there's no such thing as kinetic energy of light. All right? So just so you know that they have a range of. Okay. So in this video, you have looked at what is baryon and Lepton number, okay, and also how nuclear reaction, when you write them, have to obey all the numbers. Okay, I have given you a detailed walkthrough of the alpha plus and the alpha minus decay about how all these numbers are balanced or conserved. Okay, and then finally, I've explained because of the presence of this antineutrino to balance the Lepton number. These two particles will share Ke. That's why your beta has a range of Ke. And when thinking about beta particle, think about particle-antiparticle combo, number one. Number two, sometimes you can be asked about the quark conversion. So for beta minus, down to up. For beta plus, up to down. Okay. All right. So that's it for this video. And I'll see you in the next one. Bye-bye.